Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So, in previous sessions, we are discussed about the solid mechanics and material subject. In this subject, we have discussed about various types of stresses and strains and stress strain curve, and how to find the stresses in uniform bar sections. But in this session, so I want to explain about the bars of varying section. So you know how to calculate for a uniform bar section stresses. But in this section, we will study the bars of various sections, how to calculate. So the course outcome is explain the concept of stress strain, material constitutional relationship, and strain energy induced in linear, elastic, and homogeneous and isotropic materials subjected to forces. So this outcome after the end of the course, or after the completion of this module, the student should be able to explain about different types of concepts of stress strain relationships, and then explain about various cross sections, how to calculate the stresses, and what is the relationship between these the elastic constants they can able to answer. So in this present session, first we will discuss about stresses in bars of varying section. So here consider the another rod of varying cross section with the same axial load P as shown in figure. So here another rod means already we have discussed in previous section. So the rod is uniform bar. Suppose one rod is like this, uniform bar. So the throughout its cross section is same. So whenever this one is subjected to P, so how do you calculate the stresses? So you can calculate stress. P is equal to stress is equal to load per area. So how much load acting, and what is the cross sectional area? A. Suppose the rod having diameter D, the area is equal to pi by 4 d square. So this is in the case of uniform bar. So this one is example uniform bar. Already we have seen in a previous session. But in this, it is not uniform. Same rod. Take this one, another rod. Take the rod of varying cross section. See, with the same axial load as shown in figure. So, the varying cross section here is different, here different and different. So, gradually this decreased the area. This type of bar is called as varying section. So, how do you calculate stresses here? First, you take the elemental cross section. So, that is with dx. With x distance, you take the elemental area. So, this is called elemental area. So, take this one subjected to axial load. So, that is in elongation dx plus d delta. So, you can write like this, with x distance from its support, take a small cross-sectional area. So, find the stresses on this elemental area. So, let us take an infinite element of length dx in the rod that undergoes a deflection d delta. due to load P. So take this deflection d delta and elemental of length dx. The strain in the element is, how do you calculate? The strain is change in length by original length. So your change in length is d delta. The original length is dx. The original is dx. The change in length is d delta. So change in length by original length, and here you can take d delta is equal to epsilon dx, that is strain in the element. So the deflection of total length of the rod can be obtained by integrating above equation the deflection of total length of the rod. Now we have taken for small length of the rod. So integrating the above equation with limits 0 to L. So delta is equal to d delta is equal to epsilon dx. So integrating the above and integrate this dx, so you will get delta integrate epsilon dx. Limits are 0 to L. So here, as per uniform power section equations, we know the strain is equal to, you can write delta L is equal to PL by AE. So delta L by L, that is strain. So we can write in terms of dx. So here length is dx and E AE. A is cross-sectional area with x distance. So you can write like this. So as the cross-sectional area of the rod keeps varying, it is expressed as a function of its length. So if the load is also varying along the length, like the weight of the material, it should also be expressed as a function of distance. That is phi of x in equation. So if the load is also varying along the length, like the weight of the material, so that also in expressed as a function of distance. That is px in equation already shown in this px, E into x. Now, if the structure consists of several components of different materials, then the deflection of each component is determined and summed up to get the total deflection of the structure. So if the structure consists of several components of different materials, suppose this is one structure, this is having the combination of 2-3 materials. So material 1, 2 and 3 and different with different cross-sectional area. So deflection in each component separately need to calculate and then sum up to get the total deflection of the structure. So when the cross-section of the components and the axial loads on them are not varying along length, so the total deflection of the structure can be determined by using this formula. So I 1 to n So number of components, several components are there up to 1 to n and PL by AE. So first P1L1 by A1E1 and P1L1 by A1E1 plus P2L2 by A2E2 and so on. So that is summation will give deflection P1 by L1 and E1 E1 plus P2 by P2L2 A2 E2. So simplify Li by Ai EL. So example shown in this figure is variable cross section, but two bars are different, two components, different materials. That is aluminum having modulus velocity is 70 gigapascal and steel the modulus velocity is 200 gigapascal. So here the load acting 10 kilonewtons downwards and 25 kilonewtons at B point. At A point 10 kilonewton, at B 25 kilonewton. The length is 0.4 mm and 0.5. So in this, need to calculate stresses. So E is equal to 70 gigapascal converted into Pascal, 10 to the power of 9 Pascal. 2 into 10 to the power of 9 Pascal. So 1 Pascal is equal to 1 Newton per meter square. So 1 Pascal. Clear? So now calculate stresses. Consider a rod ABC with aluminum part AB, steel part. As shown in figure, AB and steel part BC, aluminum AB and then steel part BC, having diameters 25 mm and 50 mm respectively. So the diameter of the rod, so diameter, the first one diameter is 25 mm and this BC diameter 50 mm respectively as shown in figure. Determine the deflections of points A and B. So what is the deflection at point A and what is the deflection at point B? So here shown 10 kilonewtons acting at A and B is 25 kilonewtons. 25 plus 10, 35 total load acting here. Now deflection of the part AB. How do you calculate the part deflection here? Delta P1 L1 by E1 E1. So what is the load here? So that is PAB into length of AB, area of AB into elasticity, modulus of elasticity of AB rod. So calculate here. AB and this one AB. So now calculate what is the load acting at AB point? 10 kilonewton. into 10 cube into length. What is the length here? The length of the AB. The AB point length is 0.4 mm. So given in mm here, and then area of the rod 5 by 4 d square. What is the diameter? The diameter is 25 mm. And the elasticity of modulus E is equal to 70 into 10 to the power 9 gigapascal. 70 into 10 to the power 9. So solve this, simplify, you will get a deflection of AB. Similarly, deflection of part BC is equal to PBC, length BC by area of BC into modulus of velocity BC. So now the PBC, the BC load is 35 kilonewton. 35 into 10 cube into length. Length is 0.5 mm. The area 5 by 4 into 50. And here E value is 200. Gigapascal, 10^9. So solve this one, you will get deflection at part BC. Similarly, deflection point of B. What is the deflection at point B? And deflection of point B is already seen here, and the deflection of point A. So whatever occurred at BC at this point, so that is deflection at point B. And then deflection of BC. So A is add this deflection BC plus deflection of AB. Summation. So we will get deflection at deflection of point A. So like this, need to calculate the deflections of deflection or stresses in varying cross sections. Stresses in bars of statistically indeterminate problems. So when it is said to be indeterminate problems, members for which reaction forces and internal forces can be found out from static equilibrium equations alone are called statically determined members or structures. The problems requiring deformation equations in addition to static equilibrium equations to solve for unknown forces are called statically indeterminate problems. So statically determined problems means the internal forces and reaction forces can be found out from static equilibrium equations. The problems requiring deformation equations in addition to static equilibrium equations to solve for unknown forces are called statically indeterminate problems. So here shown examples for statically determined and statically indeterminate. So here statically determined problem given, but in this the forces or internal forces can be found out from static equilibrium equations So in this, both sides are faced, some reaction forces will be occurred, induced in the reaction at supports, at their supports. And also internal forces also acting. So these type of problems are statically indeterminate. In addition to this determined problems, need to calculate some deformation, the internal deformation and external deformation due to the reaction forces. Here load is acting external, but here load is inside. These type of problems are called statically indeterminate problems. For these problems, so the consider equilibrium equation in the vertical direction for determining the algebraic sum of the forces. So reaction force at the support for the bar ABC is shown ABC. So the summation of vertical force is equal to 0. Therefore, the reaction force minus internal force will be 0. So now consider the right side bar M and O in figure, which is rigidly fixed at both the ends. In this M and O, both ends are fixed. For this, from static equilibrium, we get only one equation with two unknown reaction forces R1 and R2. Two equations are there, R1, R2 minus P. For equilibrium, for static equilibrium, so the summation of all forces, external and internal, will be 0. So hence, this equilibrium equation should be supplemented with a deflection equation, which was discussed in the preceding section to solve for unknowns. If the bar M1O is separated from its supports and applied the forces, then these forces cause the bar to undergo a deflection R1 to R and P. R1, 1, 2, R1 and R2 and R and P. Then deflection at MO that must be equal to 0. So the delta Mn plus delta MNO is equal to 0. These two are delta Mn and delta NO are the deflections of parts Mn and NO respectively in the bar MNO. So individually these deflections are not 0, but the sum must make it to be 0. The individual deflections are not 0, but the summation of these two, so delta Mn and delta NO. But while calculating individually, we are taking the deflections are not 0. Whenever you are taking the summation total for entire rod, it make it to be 0. So the above is called compatibility equation. So which insists that the change in length of the bar must be compatible with the boundary conditions. The deflection of parts Mn and NO due to load P can be obtained by assuming that the material is within the elastic limit. So delta Mn is equal to R1L1 by A1En. So here R1 is the reaction force. Instead of P, here reaction force is acting. Actually this one is PL by AE at Mn. Similarly at NO, R to L2 by A to E. So statically, for indeterminate problem, substituting this deflection equation R1 L1 minus L1 by A1 E1 by E minus R2 L2 by A2 E is equal to 0. The combining equations R1 and R2 P A1 L2 by L1 A2 plus L2 A1. Similarly for R2 P A2 L1 by L1 A2 plus L2 A1. So from this equation reaction forces, the stresses acting on any section in the bar can be easily determined. So example 2, the stresses in non-uniform bars. Consider a bar of varying cross section subjected to tensile force P. So this one also non-uniform bar. So already I explained in previous case. Delta X, take elemental cross section. The throughout the length is the bar is L, but you take with X distance what is the deflection. So let A cross sectional area of the bar and choosing section XS. So you can calculate the stress is equal to load per area. So if E Young's modulus of the bar, then the strain at the section can be calculated by using delta L is equal to PL by AE. See in this shown the calculation equation part, thus the extension of entire bar delta is equal to 0 to L P by E into delta X by A. So let us consider such a bar as shown in the figure below. The weight of the bar being supported under section XX. Under XX, see the weight of the bar being supported. So like this, you can integrate 0 to X rho Ga dx, where rho is the density of the bar and the stress at XX is like this. Whenever you calculating the weight of the, you are considering the weight of the bar also. So stress is equal to load, whatever load acting externally plus due to the self weight. So at this, you will get the equation P plus 0 to X rho into G into A into dx, the gravitational force and the area. So differentiating the above equation with respect to X, so we get sigma dA by dx into rho G. So simplify this equation, so we will get dA by A is equal to rho into G by sigma into dx. So integrating the above equation, we get integrating dA by A is equal to integrating rho G by sigma into dx. So A is here a small elemental cross-sectional area at section XX. So in this, we are calculating the stress at cross section while considering the weight of the bar. So log Ex. So when after integrating, you will get. So after, in order to determine the constant of integration, so apply boundary condition. The boundary conditions are at x is equal to 0, a is equal to a naught. So log Ex, log Ea. So what is the value at boundary condition A naught. Substitute in this equation. So we will get finally E into rho g x by sigma, that is equal to A by A naught. And also at x is equal to 0 boundary condition. So area is A naught and x is equal to 0. For this diagram, see, at x is equal to 0 and then delta x, and area is small a, but this area at x is equal to 0, A naught. Clear? So now thus find out sigma value P by A naught. So thus A by A naught is equal to, so already we have written here A by A naught. A by A naught is equal to e to the power of here rho g x by A naught by sigma. Actual equation is, the actual equation E rho g x by sigma is equal to A by A naught. So in this substitute sigma value g into x, A naught multiply divided by P. Why? Because here sigma is equal to P by A naught. Here given in this equation sigma is there just. So you are writing here load upon area at O at 0. So we will get A by A naught. Okay. So like this, so you can calculate stresses in bars of varying cross section and indeterminate and statically determined and statically indeterminate problems. Non-uniform bars also you can calculate. So by using these equations, you can calculate stresses acting at any section in the bar can be easily determined. These are the references I have taken. Ramamurthu, Strength of Materials title, in publication is Dhanapati Rai Publications. Similarly, R.K. Rajput, the title is Strength of Materials. Echand and Co., the publications in New Delhi. Now, R.K. Bansal, the title is Strength of Materials, Textbook of Strength of Materials. Publications are Lakshmi Publications. And then R.S. Kurmi and Gupta, Strength of Materials. And publications are Sound Publications. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.